Hi everyone, in this video we're going to go through section 6.5 called least squares problems. And this section is kind of cool. If you've ever done any statistics in the past and talked about a least squares regression line or just regression lines in general, this section lays the foundation for why all of that is correct, basically, for why a best fit line is literally the best fit in a model when it's a least squares line. And our goal in this section is to solve an inconsistent system. Well, how are we going to do that? Our goal is to find an x, find an x vector that makes ax as close as possible to a vector b. All right, so ax equals b may not have a solution, but we're going to find a vector x that is as close as possible, or ax is as close as possible that we can get to b. So how do we define as close as possible? Well, our definition here for least squares solution, we have a matrix m by n, a vector b, and a least squares solution of ax equals b is a vector x hat. So we're using this hat on the vector there in Rn such that b minus ax hat, the distance between, or the length of that vector, the distance between those two vectors, is smaller than b minus ax, the length of that vector, for all x, any other vector in Rn. Okay, that's how we define as close as possible, and it's called a least squares solution. Okay, so that's all very abstract, all right? And what I want to do is draw a picture that will hopefully make it maybe a little bit more concrete. And so I'm going to draw this plane-looking guy here, and that's going to represent the column space of some matrix A, right? In the column space is a vector, the 0 vector over here. Actually, let's make that a little bit higher in my picture. This is the 0 vector right there. And we're going to put B off of there. We're going to put b vector b up there. It's not in the column space of A, so ax equals b would have no solution. Okay, but within the column space, there's, let me change colors here, there's some vector over here that might be represented as a times x1. X isn't supposed to be a subscript. The 1 is. ax1. There might be some vector over here that is ax2. All right. There might be some vector somewhere else that's ax3, but there is a vector in the column space. It's going to be right there. That is, we'll deem as ax hat, and the length of this vector, b minus ax hat, is less than or equal to the length of any of these other vectors here. Okay, so that red distance is smaller than any of the green distances. That is called a least square solution, and that's what it looks like. All right, so in our next step, we're going to get a little bit more abstract and general in our notation. Let's start out with, we're going to say let b hat, so we're going to have a couple of different hats here. B hat be the projection, the orthogonal projection of vector b onto the column space of A. Ultimately, this process will lead us to our formula, but we've got to kind of build and understand how we get there because that gives it more meaning. Okay, so we're projecting B, just like in the picture above, onto the column space of A, calling that vector B hat, that is the red dot vector AX hat. All right, and we're going to say because B hat, B/C for because, B hat is in the column space of A, we can say that AX equals B hat is consistent. So first we know that it has a solution because it's in the column space. And there is an X hat, a vector X hat in Rn such that A times X hat equals B hat, right? That's stating what I drew above. Formally, we know that vector exists. We can orthogonally project. We've done that now in a couple sections, and we're just going to name that vector AX hat. We're naming it B hat, and how do I get there? I multiply matrix A times some vector to get there. I can solve that system. So then we'll say since B hat is the closest point in column space of A to B, is the closest point in col A to the vector B. A vector x hat is a least squares solution S-O, there we go, a solution of AX equals B if and only if it satisfies AX hat equals B hat. All right, so now this is tying in the language from the definition. B hat is the closest point in the column space, so it is, by definition, a least squares solution to that equation. Okay, and then I'll just state kind of a closing thought with that before we get to how we build the formula. X hat is a list of weights that builds B hat out of the columns of A. Okay, so that's what that X hat represents. Okay, so that part is understanding the what it is. Now we get to breaking down where the formula comes from. So let me draw a little line there. Now suppose that X hat satisfies AX equals B hat, AX hat equals B hat. So suppose that that vector exists and it's there by the orthogonal decomposition theorem, which we've come across previously. Decomposition theorem, abbreviate that, THM for theorem. B hat has the property that B minus B hat is orthogonal to the column space of A. Right, that's that vector. What color was it up above? That's my red vector up there. That is orthogonal to the column space. Okay, and then, so we can say, so B minus AX hat, we're just making a substitution there, is also orthogonal to the column space, right? Just make that substitution AX hat equals B hat. All right, so given any column A sub J, representing a column of matrix A, the columns of A are orthogonal to that B minus AX hat, so that vector, AJ, that column in A, dot B minus AX hat has to equal 0. That one column dotted with the vector that it's orthogonal to has to equal 0. And I can write that dot product as a regular product. That column transpose times B minus AX hat also has to equal 0. Right? I can turn a dot product into a multiplication problem by taking the transpose of that vector. Then it follows that capital A transpose, if every single column, right, has that property because it's orthogonal, capital A transpose all of the matrix times B minus AX hat is equal to 0. All right, so we're going to distribute first. A transpose times B minus A transpose A X hat equals 0. And then we'll just rewrite this a little bit differently, add the one negative term to the other side, and write it in our formally stated conclusion. A transpose A times X hat is equal to A transpose times B. And that's where we were heading. A formula for how we can find this vector x hat. On the left-hand side, I take A transpose A. On the right-hand side, I take A transpose B, and then I can solve this system to produce the vector x hat that is the least squares solution to AX equals B. Now our theorem states what we just built on the previous slide, theorem 13, the set of least squares solutions of AX equals B coincides with the non-empty set of solutions of the normal equations A transpose AX equals A transpose B. That's what I built on the previous slide. Here we have it stated as theorem 13. Now let's go through an example where we solve and find the least square solution. Now that we're told that it's an inconsistent system, AX equals B, and I've shown this off to the right here. I did this work before I started recording, right? We can see from in the third step, we get the bottom line saying 0 equals negative 21. That is false. This system is inconsistent. So our goal in this section is to find the least squares solution. All right, so how do we do that? Well, we have a couple of steps of preliminary work, and then we solve we solve a new system of equations. Okay, the preliminary work is to find A transpose times A. All right, that's first. A transpose looks like this: 4, 0, 0, 2, 1, 1 times regular A, 4, 0, 0, 2, 1, 1. That's a 0. And when you do that multiplication, you get 17, 1, 1, 5. We also have to take and find A transpose times B. A transpose B is 4, 0, 0, 2, 1, 1 times my B vector, 2, 0, and 11. Do that multiplication, and you get, let's see, 19, 11, 1, 9, 1, 1 there. Okay, that is my preliminary work, and so now the last step is to solve this system using your calculator, using row operations, whatever you want. 17, 1, 1, 5 times x1, x2 is equal to 19 and 11. And if you solve that system, you find that x hat, that will have a solution. It has to have a solution. X hat is 1, 2. Okay, that's it. Find the least square solution. There it is. X hat is called the least square solution. It is not the solution to this system because it's inconsistent, but it is close as I can get to that solution. To that, excuse me, not as close as I can get to that vector B. Here we have a massive looking system, all crazy and everything. If you want to pause the video, maybe you did in the last one, and try this one ahead of time before I write down all the answers and do the work for you, you could feel free to do that. That might be a good challenge. But let's take, and I'm just going to jump right to what is A transpose times A. Okay, so my goal is to find the least square solution. So I do this preliminary work, 6, 2, 2, 2. And then 2200, 2020, and 2002. There's A transpose A, and then A transpose B should just be a single vector always. 4, negative 4, 2, 6. So I'm going to jump right to my augmented matrix here with my 6, 2, 2, 2, 2, 2, 0, 0. 2, 0, 2, 0, 2, 0, 0, 2. Augment that with my last column, 4, negative 4, 2, and 6. Maybe put a dotted line there if you want. But when you type this into your calculator, you get that this guy is row equivalent to, let's see, 1, 0, 0, 1, 3. 1, 0, 0, 1, 3. There's my dotted line. 0, 1, 0. Negative 1. There's a 1 right there. Negative 5. And then 0, 0, 1. This is negative 1, negative 2. And what we find is that this isn't nicely in, we don't have a solution for every variable. This is a dependent system, okay? And that can happen. I said a minute ago, you're guaranteed to get a solution, but not necessarily just one. Okay, so here we have a dependent system. We have a free variable, x4 is a free variable. And so our least square solution looks like this when you do the work, the finishing work that we've done a bunch of times before. It's 3, -5, -2, 0, plus x4, my free variable, times -1, 1, 1, 1. So any point on that line, basically, is a least square solution to that original ax equals b. It's as close as we can get to the solution. This next theorem brings back some terms that we've encountered at various points in the semester, and just states them as they relate to this topic. If I have an m by n matrix, the equation ax equals b has a unique least square solution for each vector in Rm is logically equivalent to the columns of A are linearly independent, and that is logically equivalent to A transpose A is invertible. So in the first example, A transpose A was invertible, and we got a unique solution. In the second example, A transpose A was not invertible. We lost a pivot, and our solution was not unique. Okay, so those are all logically equivalent, those three statements. Just kind of like bringing back the invertible matrix theorem, but for this slightly more complicated topic. In this next example, we're going to look at how close our solution is, okay, to the b vector. What is the error in my least square solution? And so to do that, we have our same matrix A and our vector b from the first example, right? That system is consistent. Okay, but the steps that we take to find our error, how close is our best approximation, is we're going to take and find first A times x hat. So that is our matrix A, 4, 0, 0, 2, 1, 1, times the vector x hat. And that's going to equal b hat. But when you do that multiplication, A times x hat is equal to 4, 4, 3. And from the notation earlier, this is the vector b hat. That's in the column space of A. That's technically as close as we can get to the vector b. So how close is it? We're going to take now and find what is b minus. What is b minus A times x hat? That is that orthogonal vector. I believe it was red from the first picture that I drew for you. We find that orthogonal vector, and it's -2, -4, 8, and then the length of that orthogonal vector, b minus ax hat, is equal to the square root of 2 squared is 4, 4 squared is 16, 8 squared is 64. Add them up and you get radical 84, which is, I think, 2 root 21, or if we approximate that, you get 9.2 to the nearest 10th. Okay, so off by quite a bit, but any other vector, ax1, ax2, right, any other numbers that you multiply, any other vector that you multiply by matrix A will produce a greater distance, will be further off than that 9.2 that we just got. All right, this last example in this section pieces together two things that we've been doing in Chapter 6 and allows us to more efficiently find this b hat vector. So we're finding a least square solution of ax equals b. Starts out the exact same way, but what I want to note about my matrix A, take a look at it, pause the video if you want to, and see if you can notice something special about A. And if you unpause it, the vectors of A, they are orthogonal to each other. The columns of matrix A are orthogonal to each other. A is orthogonal, right? If you take the first column dot the second column, it's you get 0. The significance of that is I don't need to write and solve that system that we did in the first two examples. I can jump right to my b hat vector because there's a formula for the orthogonal projection when I have an orthogonal basis. It's b dot a1 over a1 dot a1 times a1. Remember that formula? This is a1. Plus b dot a2 over a2 dot a2 times a2. We're orthogonally projecting the vector b onto the column space of A. And because the column space is orthogonal, there's a nice convenient formula for that. So the dot products, you get 8 over 4 times A1, oops, not equals, plus 45 over 90 times A2, that is negative 1, 1, 5 halves, and 11 halves when you simplify it. Okay, that's the B hat. A times X hat equals B hat. So then the last step is you can do this right in your calculator. Solve for X hat, 2 and 1/2. Take your matrix A, augment it with the B hat column that we just found, and solve it, right? You use your calculator, right? Or, I mean, you could do it by hand. It wouldn't be terrible, but a little bit quicker if you use your calculator. Okay, and again, that was simpler because our matrix A was orthogonal. The columns were orthogonal to each other. Now, there is one more Theorem 15 and one more example in this section, and I'm going to choose to not do them and not include them in the video, and you won't be assessed on them either. So that is it for this video. Thank you very much for listening. Work on some homework. Let me know if you have questions, if there's something that was unclear. A lot of the work I didn't go through the computation, the dot products, the row operations, but you could use your calculator to support you to do that. Hopefully you're there by now with that comfort level. But please, if you do have questions on some of the things that I didn't show explicitly, let me know and we can go through them. Thank you for listening. Have a wonderful day.